Okay, so we'll give an example of a ring which is a UFD but not a PID. And what is that? That is ZX. So ZX is a UFD but not a PID. Okay, we have already proved that this is a UFD in the previous section. The last topic of the previous chapter, we have already proved that this is a UFD. We now need to show that it's not a PID. What does it mean to say that a ring is not a PID? Or an integral domain is not a PID? Yeah, exactly. So there should be an ideal which is not a principal ideal. We should show that there is an ideal which is not a principal ideal. And the ideal which we are going to take, any idea? Okay, I had told you all to remember this ideal. Which one? Yeah, x comma 2. Okay, consider the ideal I equals x comma 2. Okay, and we proved that this ideal is essentially, you can quite easily see this, but we proved that this ideal is essentially the set of all polynomials, exactly, with even constant terms. Okay, this is going to be quite easily, you can show that just by set containment on each side. You can show that this is the set of all polynomials with even constant term, even. I'm going to prove that this is not a PID. So how do I prove it's not a PID? I assume it's a PID, get a contradiction. Okay, so suppose this is a PID, that means it is generated by a single polynomial. What will happen here? This will mean that x is in this and 2 is in this, right? X is in this and 2 is in this. What does it mean to say that x is in this? Yeah, that means you can write x as p of x times something, or in other words, p of x divides x. Actually, what I want to use here is p of x divides 2. So let me say that. Okay, now what are the possible divisors of 2 in ZX? Yeah, which ones? What are the possibilities? In ZX, what are the possible divisors of 2? Yeah? Yeah, that's right. Yeah, plus and minus 2 and plus and minus 1. Okay, so plus and minus 2 and plus and minus 1. That's quite obvious, right? Because what does this mean? You can write 2 as p of x times q of x. Okay, now you make a degree argument here, right? The degree on the left is 0, so the degree on the right should also be 0, which means that the degree of p of x should be 0, right? And the degree of q of x also should be 0. So these are like integers. So therefore, it should be an integer divisor of 2, and the only integer divisors of 2 are plus and minus 1, plus and minus 2. So simple enough to make that argument that p of x would either be plus and minus 1 or p of x would be plus or minus 2. Now, if p of x is plus or minus 1, what will I be? All of z, all of zx, right? Because these are units. That will give us a contradiction. Why? Because this is not all of zx. How do I know that this is not all of zx? Which polynomial? Can you give me one polynomial which is in zx but not here? 1. Okay, there are lots of polynomials. 1 is one polynomial, x square plus 3 if you like. Okay, any number of polynomials. Select one and show it's not in this, because this is the set of all polynomials with even constant term. One has odd constant term, so that would work. Okay. What about if p of x is plus or minus 2? If p of x is plus or minus 2, what happens to this? What type of polynomials you will get here? All the terms will have to be even. right? Because everything that's in this would have to be a multiple of p of x. So therefore all terms would have to be even. Okay. Again you'll need to say that, now you'll have to say that I is not this. That means, can you find an element from here which is not here? Can you find an element from here which is not here? X, right? X cannot be here. Correct? X is here, but X cannot be here. Why X is not here? Because suppose 2, let's say you can check minus 2 also, but suppose X divides 2, what would this mean? That means you can write 2 as X times some p of X. This is never possible because this is a, I'm making a mistake. 2 divides X, sorry. 2 divides X. Okay, but now what you do is, this will mean that this polynomial is a polynomial of degree 1. If you make a degree argument, this will mean that this polynomial is a polynomial of degree 1. So something like ax plus b. Okay, comparing the coefficients, you will now see that 2a should be 1, which is not possible. Okay, 2a cannot be equal to 1 in z. There is no integer such that a times 2 is 1. It's a rational number, but no integer. Okay, so that gives you a contradiction on both sides. So therefore, this cannot be a PID. Sorry, this is not a principal ideal, and hence Zx is not a PID. Okay, so that's a simple argument to show that Zx is not a PID. Okay, so now we'll look at the next interesting type of integral domain, that is the Euclidean domain. Okay, so the idea of the Euclidean domain comes basically from division algorithm. Okay, the idea of division algorithm. So what this has is, so we say that a integral domain is a is a Euclidean domain if you can find some function on that integral domain which satisfies some properties. Okay, let us see which ones. So an integral domain D is said to be a Euclidean domain if there exists a function, okay, which we call as the measure. Okay, we call this as the measure. There exists a function d, small d, from d to I think we want to go to n union 0, or from d difference 0 to r plus, sorry. Okay, such that, so I'm not defining this at 0, okay, which has the properties that, 1, if a and b are in d difference 0, okay, then d of a is less than or equal to d of ab. And the other important one is, for any a in D or a comma b in D, where b is non-zero, I should be able to divide just like how we do in division algorithm. Okay, there exists uniqueness is not required. Okay, there exists q and r in D such that a can be written as bq plus r, where, okay, so this is how this behaves like the degree. So where d of r should be less than d of b. Okay, the d of the remainder should be less than the d of the divisor. Okay, just like in so you can see that's like the degree in fx. Okay, or r is 0 itself, one of the two things. We don't define d for the. There are two Euclidean domains which we are familiar with. Okay, one is z. Okay, can anyone tell me what's the measure on z? Yeah, yeah, who's that? Yeah, so and what's the measure on fx? What is the measure on fx? If f is a field, what would be the measure on fx? I'm saying that there are two obvious Euclidean domains. One is z, the other one is fx. For any field f, fx is a this thing. Z, the measure is okay. Why? You take d from z difference 0, you need not define it from z difference anyway, to r plus, okay, defining d of a to be mod of a. Check that both these conditions are true. Okay, here you will get equality in case of z, so it's fine, no problem. And how do you get this? How do you get this part? From division algorithm. Take any two elements a and b in z, where b is non-zero, you know you can find this using division algorithm. Where r is less than, r is positive, you can find an r positive in that case. So r is positive and r is less than mod of b, which is the d of b. Okay, so that's one Euclidean domain. The other one is fx, where f is a field. Okay, in this case, what is the measure? Can anyone tell me? D of any polynomial fx, what we will take it to? Difference 0, very important, otherwise it won't work. What will take it to? Yeah? Yeah, the degree, right? The degree of fx. And why? So let's check why this is true. What happens to degree of fx into gx? It is degree of fx plus degree of gx, which is definitely bigger than the degree of fx, right? Degree of fx into gx is degree of fx plus the degree of gx, which is definitely greater than or equal to the degree of gx. Okay, in fact, it is strictly greater than. No, not strictly greater than. If one is constant, then it's a problem. Okay. What about if I take two polynomials fx and gx such that g is non-zero? I know by division algorithm that I can do all of this, just replacing d by the degree. Okay, r is the remainder polynomial. Okay, so we have two Euclidean domains. So we can prove something by the we can try to catch hold of units in a Euclidean domain using the measure. Okay, kind of imitating what we did with that n function in z root d. So let's see. What do you think? How would I be able to catch hold of the units depending on the measure? So I want to say that let D be a Euclidean domain with measure D. Then I want to say that U and D is a unit if and only if there is some condition on d of u. What is it? Equal to 1? You think so? Notice what happens here. What happens to the degrees of units? What happens to the degrees here? Degree of units are 0, right? So that's not true. It can't be 1. No, not even less than 1. The d is actually a scalable kind of a function. You can, if there is one, this thing, you can always scale it up and down quite easily just by multiplying a c to it. So not really going to work in that way. Yeah, any idea? Okay, so this happens if and only if this degree is this, if d, the measure of u, is the same as the measure of 1. What happens is, for sure, using this property, you know that the unity element, right, is going to be of least degree. Why? Why is the unity of least degree? Just look at this, right? If you take x as any element in D, right, then D of 1 would be less than or equal to D of 1 times x, which is D of x. So that will be the least measure will be attained at 1, okay, and every other unit. So anything else is going to have a measure bigger than 1, the D of 1, okay. So how do we prove this? So assume that this is a unit. If u is a unit, okay, what happens? There exists some v in D such that u into v is 1, okay. So is it okay? Okay. So what happens is d of u will be less than or equal to d of uv, but this is nothing but d of 1. So we prove one side of the inequality, and as I told you, the second side is obvious. This happens for everything. D of 1 is always going to be the least measure, okay. So also what we have is d of 1 is less than or equal to d of 1 times u, which is nothing but d of u. So that gives us the second part of the inequality. From these two, d of 1 is equal to d of 2. What about the other side? D of u is equal to d of 1, okay. What about, suppose d of u equals d of 1. I want to say that u is a unit. How do I catch hold of its inverse? How do I catch hold of its inverse? Right? So this property tells us, okay, that given any two elements in the integral domain b naught 0, I have these elements q and r such that this happens, okay. So let us divide what? We are attempting at doing what? We are trying to find a v so that 1 is equal to u times v. So what are we doing? What are we doing? We should divide what by what? Yeah? Okay? 1 by? Yeah, we should, not by v. We should divide 1 by u and show that when you divide 1 by u, okay, that quotient you want to show is the inverse. Hence, all you've got to show is that the remainder is 0. Okay, you've got to show that the remainder is 0, and I think that is quite easy to see. So suppose this happens, there exists a V in V comma R in D such that U equals 1 is equal to U times V plus R, where what? Where D of R is less than D of U. Okay, where D of R, where there are two possibilities, either R is 0 or D of R is less than D of U. But what is D of U? It's given to be D of 1. So this is saying that D of R is strictly less than D of 1. As I said, that cannot take place because D of 1 is going to be the least possible measure. So if this cannot take place, therefore that has to take place. Let's write it out. So I'm going to show that this is not true, and therefore this will be true, and we got a proof. Okay. So suppose D of R was strictly less than D of 1. We know that D of 1 would have to be less than or equal to D of 1 times R by definition, which is D of R, and that gives us a contradiction, right? Because here we have this is strictly less than and this is less than or equal to. This cannot take place. Both these statements cannot hold simultaneously. Okay, so this is a contradiction, which means that D of R cannot be strictly less than D of 1, and therefore there is no other option but R should be 0 and 1 should be equal to U times V. So we got an inverse. Okay, so if you want to check whether elements in a Euclidean domain are units, simply check whether the measure is the same as the measure of the unity element. Okay, that's one way of looking at it. Okay, now should I do this first? I'll come back to that later. Let's prove that every Euclidean domain is a principal ideal domain. Okay, we'll prove that every Euclidean domain is a principal ideal. Very simple proof to this. In fact, this simply imitates the proof of showing that showing that fx is a PID. Okay, exactly you imitate the same proof. Okay, let's see how we do that. We'll go over the so every Euclidean domain is a PID. So let D be a Euclidean domain with measure D, small d. Okay, I want to say it's a PID. That means I have to take any of its ideals and show that it's a principal ideal. Okay, let's attempt and see what we did in fx. So let I be an ideal of D. Okay, of course there are two possibilities. One is the case when I is 0 itself. If I is 0 itself, what is it generated by? By the 0 element. So it's a principal ideal. Okay, whatever the case when I is non-zero, I need to take this separately. Okay, what did we do in fx? Does anyone remember? How did we show that any ideal in fx is a principal ideal? Do you remember? How did we get the generator? Yeah? How we got the generator of an ideal in? Yeah? That's right. So we using well ordering principle, right? So we know that we looked at all possible degrees of polynomials in that, and then you pick out a polynomial of least degree. That polynomial of least degree was the generator. Okay, how do we imitate that same thing here? Exactly, you take the element, the of course it has to now be non-zero element of least measure. Okay, since this is non-zero, how do we catch hold of least measure? Just a second, I think I have made a error here. This would not work. I can't get least measure if I I made a mistake, by the way. Just correct something. I have made an error. You don't, the measure is not a function from D to R plus. Okay, this does not work. It is a function from D to N, union 0. It's not even R plus, definitely does not work. Okay, this is not this thing. It needs to be from D to N union 0. Yeah, from D to N union 0, not R plus. It will not work. Up to now, whatever we've got is from D to N union 0. So there is no error otherwise, but you need to define it correctly. Is that okay? It's a function from D to N union 0. I need to find the least element, otherwise there's a problem. If I go R plus, then you're going to have a problem here, right? Yeah? Oh yes, that is true. D difference 0 to N union 0. The codomain has to be N union 0, not R plus. It doesn't make sense. Okay, now we can take the least element. There is no problem. Wherever this is there, R plus just change to N union 0. Okay, so what we do is now we can use well ordering principle to get, because this is now D's of everything are right, are a subset of N union 0. In N union 0 we can get least element. Okay, well ordering principle, it works there. Okay, so let A be an element in I with least measure, and we can do this by the well ordering principle. Simply look at all D of C's for C in I, right? You are definitely, it's going to be a non-empty set because this is not the 0 ideal, so it has to be a non-empty set. So therefore you can find the least element and take one of the elements from there. Okay, so if you take I with least measure, what I want to show that this is generated by A. Okay, how do I show it's generated by A? Because A is an element of I, we know that the ideal generated by A is a subset of I. Take an element of I, prove that it's in A. Can you tell me how we'll do that? What does this mean? How do I show that this is in A? What do I need to do to say that this is in A? Ideal generated by A. You can write B as A times some X. Okay, how do I get this? Yeah? See, this is exactly what we have to show that. In other words, A divides B. So how do we show that A divides B? Use the property that replaces the division algorithm. Okay, so this means that there exists some, let's go with Q, just because some Q in order, anyway, Q and R in D such that B can be written as AQ plus R, and here either R is 0 or D of R is strictly less than D of A. Okay, this is a non-zero element because A is of least measure. Okay, 0 has no measure. Okay, now what happens? What would happen if this is less than A? D of R is less than D of A. Yeah? Why? So, its least measure in I. D of A. Why? Why? Reason. But R is some element in D. Why is it a contradiction? R is some element in D. Q and R are some elements in D. D of R is, I can find an element in D of lesser measure than A, there is no problem. So what did we do in Fx? What did we do in Fx? So we started with the polynomial of least degree, took any element, took any polynomial f of x in I, okay, divided. So we could write f of x as p of x times q of x plus r of x. Okay, and we had to show that r is 0. How do we do that? Yeah, you take this on the other side. So once you take it on the other side, what happens? Both f of x is in I, okay, and p of x is also in I. So therefore p of x times q of x is in I. Therefore f of x minus p of x times q of x is in I. So therefore r of x is in I. Now it's a contradiction, because now the degree of r cannot be less than the degree of p. So r has to be 0. Can we imitate the same process here? Simply take AQ on that side, right? B is in I. You've taken B in I, right? A is in I, so AQ is in I. Therefore R should be in I. That's when you get the contradiction. Okay. So as B is in I and A is in I, B minus AQ, so R equals B minus AQ is in I, and therefore D of R should be greater than or equal to D of A, or R should be 0. Okay, and therefore since we know that D of R is strictly less than D of A, write it the way you want, that's fine. D of R should be 0. So R should be 0, and therefore B should be A times Q, which is in A. That proves my theorem. Okay, so this tells us that every Euclidean domain is a PID. Okay, so we know now we have the set containment is like this. We have a Euclidean domains, PID is outside it, and UFD is outside. Okay, there are UFDs which are PIDs. We know an example. Which one? ZX. Okay, but I don't still know whether there's a PID which is not a Euclidean domain, and that I'm leaving to you. An example of this you will find on Dummett and Foote, if you like. It is one of the those Z root Ds. I think if I'm not mistaken, it's Z root 7 or minus 7. I can't recollect exactly. Okay, so yeah, now let's show that the set of Gaussian integers is a Euclidean domain. Okay, so here I have to actually define the measure. Okay. Okay, simple proof, not very difficult. So what is the set of Gaussian integers? It's nothing but z root minus 1, okay, or I. So yeah, one fact which you can show quite easily, that is Qi, which is nothing but the set of all A plus IB, okay, where A and B come from Q. You know what type of a ring is this? What type of a ring? With the usual addition and multiplication of complex numbers. What kind of ring is this? This is a field, okay, with usual addition and multiplication of this thing. You can quite easily show that this is a field. You can do all the properties. If you are ready to accept that C is a field, then you simply need to show that with respect to addition it is a subring, and with respect to multiplication it's a subring. That's quite easy to show. You can try and see. Okay, so you can show that this is a field, and obviously Zi is contained in Qi. By definition itself, Zi will be contained. Zi is what? In place of A and B, you now have only integers. This here you take all possible rationals, here you take only integers. Obviously, this is contained in that. Okay. In fact, this is the, you can quite easily show that this is actually the quotient ring of Zi. You can actually show that this is the quotient ring of, quotient field of Zi. Okay, try and see if you want. There is, look through the properties of what should be there in quotient fields. You can try and show that this is a quotient. And yeah, I'm not interested in that part, but I want to show that Zi is a Euclidean domain. So I need to define a measure on it. Okay, the set of Gaussian integers, the set of Gaussian integers by the way, this is not difficult to show it's a field. You simply multiply. Addition is obvious. When you add, you're going to get sum of rationals, product of rationals, sorry, sum of rationals, that's going to be rational. When you multiply also, you're going to get sums and products of rationals. Sums and products of rationals is rationals. So in each of the real part and imaginary part. So it's quite easy to see. Okay. So the set of Gaussian integers, you need to take A, B, X, Y inverse. That's what you need to see. Okay. So the set of Gaussian integers Z I okay, this is a Euclidean domain. Okay, and we can, I'll specify the measure with measure. So D from Zi to difference 0, of course. What I'm going to take it to, I'm going to take any n plus im2. Any idea? So this I'm going to take exactly to the same function which we had spoken about, that n function. Okay, the n function, by the way, I is simply square root of -1, so it's one of those. Okay, we had spoken about those rings, right? Z root minus Z root D. We said D is allowed to be negative also there. Okay, so this is nothing but, what was the n of A plus B root D over there? Mod of A square plus minus B square D. right? So here what it will be? Yeah, so your d is going to be minus 1, so it will be simply mod of a square plus b square, or in other words just n square plus m square. Mod is not required. Okay, so this is my, which is nothing but the square of the mod of the complex number. Okay, square of the mod of the complex number. Okay, so first I have to prove property 1. That is easy. Okay, so let you take x to be some n plus im and y to be n2 plus I m2. Okay, therefore what happens to d of xy? D of xy will be the complex mod square of x plus y square, of x and y. Okay, which we know from complex analysis that this is, or algebra of complex number. You can actually prove all these things, it's not required that you use that. Okay, but now the modulus of a Gaussian integer has to be greater than 1. If it's non-zero, the modulus has to be greater than 1. Why? These are both integers. So n square is a natural number, m square is a natural number. These have to be both greater than 1. Not both, one of them at least has to be bigger than 1. The other one could be 0. So the least it can be is 1. So this will be greater than or equal to mod of x square, which is nothing but, so this is what we needed to prove, that dx is less than or equal to dxy. That's the first property. What about second property? Second property, we need to catch hold of this quotient and remainder. Okay, so let's see how we do that. Okay, so here we are going to take aid from this. Let us see. This is a little bit tricky. I actually don't know why this choice is made, but that's the way it works. Okay, so what I want to do is I want to write y as some x times a plus r. Okay, this is what the attempt is, to write this y as some x times a plus r. Okay, so yeah. Okay, so yeah, so we know that x and y are in zi, and if x and y are in zi, we know that x and y, suppose y is non-zero. I want to divide x by y, so I need to say y is non-zero. Okay, so this will tell us that xy is in qi, but if xy is in qi, I can talk about the inverses of y in qi. That's the advantage. This is a field. Okay, so xy inverse is now in qi. Okay, and since this is in qi, I can write this out as some, let me write it as some p plus iq, where p and q are both rational numbers. Is that okay? Okay. Now, what I'm going to do is, I'm going to look at, so my p comma q is here. I'm going to look at the smallest integer near p and the smallest integer. I'm not looking at the greatest integer less than or equal to p and the greatest integer less than or equal to q. Okay, this is easy. P is here, right? So we know that it has integers on both sides. If it's not an integer, if it's an integer, you take the same p as the same. If it's not an integer, there will be one n on this side and another n plus 1 on that side. Bad notation, but what you do is take the smallest among those. Okay, the smallest among them I'm taking as n, and similarly for q, the smallest among them I'm taking as m. So q m plus 1, this will be now m minus 1. Okay, it sits inside some this thing. If it is not an integer, if it's an integer, take that only. There is one problem. You might ask me, what if p is right in the middle? Then what do I choose? So if p is right in the middle, you take any one of them. It works. Okay. If p is right in the middle, okay, if it's n plus half, you simply take either n or n plus 1. It doesn't matter. Okay. So let n be, let me write a because it's not unique. Okay. A smallest integer closest to p, and m be an integer closest to q. Okay, so either it will be the greatest integer less than or equal to the number, or it will be the greatest integer less than or equal to plus 1. One of those two it's going to be. Okay, that's what we are taking. So therefore, I'm going to now write xy inverse as, so this is the choice of my quotient. The choice of my quotient is this m and n. You can see the choice is not unique always. Okay, this is going to be n plus im plus whatever is here I'm going to subtract, that is p minus n plus I times q minus m. Okay, I hope this is okay. I have just simply added and subtracted n plus im. Is this okay? Cancel this out, cancel that out, all you get is p plus im. No problem. Right? No problem, right? Okay. Now you multiply throughout by y, what you get is x is equal to n plus im times y plus this thing here, that is p minus n plus I times q minus m times y. Okay. So what I'm going to say is that this is the quotient and this is the remainder. Okay, that's what I'm going to say. I'm going to say that this is the quotient and this is the remainder. Okay, so to say that this is a fair division, all I have actually got to say is show that d of this part is less than the d of, sorry, y. If I show that d of this part is less than d of y, I am done. I'll tell you why. By the way, this is Gaussian integers. This is from Gaussian integers. This is from Gaussian integers. Hence, on this side, what is there is also on an element from the Gaussian integers. Right? These are rationals. But once you subtract in order to do everything, take the product with y, it's going to be from Gaussian integers. Why? You just take this on that side, right? That's all it is. Okay. So that is from Gaussian integers. Okay. Yeah. So here's the trick. Nothing really difficult in this. So there are two possibilities. Of course, one is if this is 0, then we've got nothing to prove. If this is 0, is it okay? You take r to be p minus n plus I times q minus m into y. Okay? If r is 0, there is absolutely nothing to prove. We are done. Okay? If r is 0, there is nothing to prove. What do we need to show? We need to show that d of r, we need to show that either r is 0 or d of r is less than d of y. If r is 0, there is nothing to prove. So assume that r is non-zero. If r is equal to 0, then there is nothing to prove. hence assume that R is non-zero. Okay, so therefore what happens? What will be d of R? It will be nothing but d of p minus n plus I times q minus m into y, which is, by definition, this is nothing but the mod square of the number. Okay, so this is mod p minus n plus I times q minus m. Okay, I'm going to times y whole square, but this is mod p minus n square into y square. Okay, but what is the mod square of this? By definition, what is this? Complex. Mod square for complex number. What is mod of a plus ib square? A square plus b square. So this is nothing but p minus n the whole square plus q minus m the whole square times mod y square. Okay, but see how we have taken this n and m. We have taken this m and n in such a way, so we have taken this n to be this integer closest to p. That means the distance between p and m will be less than half. Okay, the distance between p and n will be less than half. Hence the square of the distance will be less than 1/4. Similarly, the distance between q and m will be less than half, right? It has to be. It's going to lie in this, right? So it's going to, the distance between p and n will be less than half, hence the square of the distance will be less than 1/4. So this distance will be less than 1/4 plus 1/4 times mod y square, which is half of mod y square, which is d of y. Okay, this number strictly less than d of y. Okay, so that's the proof. So how you saw how we got hold of the quotient and the remainder. What was the quotient? You have to look for the xy inverse and then look for the smallest integers near p and q. That's how we get the quotient. Okay, and remainder was simply y times this part which remains. That's the way we got hold of it. Okay, so this proves that the set of Gaussian integers is a Euclidean domain, which also means that it is going to be a PID and hence a UFD. We can stop here.